Okay, YouTube, the goal of this video will be for us to be able to quickly sketch graphs of exponential functions using basic knowledge of, say, their parent functions here. So we have some exponential function, f of x equals our base 3 to the power of x. So this is exponential due to the fact that we have an x in the exponent. And I also noticed that the coefficient of x here is a positive 1. So we're going to have some exponential growth. So looking at this, if I said, well, how would I make its graph very, very quickly? What we could say is that any graph that is exponential, and what you're seeing here is f of x equals a to the x, where our a value is specifically equal to 2. You can see that if I were to make our a value 3, like the one we have here, we could see that our exponential growth function still looks like it's in the family of exponential growth functions. As a matter of fact, the bigger I make x, it still looks very, very similar to its parent function. It's just that some key points are changing. That is, we could plug in some extra x values to show that it's really just going to kind of get steeper the bigger our base gets here. But in particular, we could say that all exponential functions, we seem to have an asymptote on the x-axis, and they all go through this point 0, 1 as our intercept. So in order to make this graph, the very first thing we want to do is we want to indicate that there's a horizontal asymptote at y equals 0. So we're going to go ahead and put that on the graph. We would say at y equals 0, or on the x-axis, we have something that is a horizontal asymptote here. Also, we would say that if I wanted to graph this, I could plug in some x values to find some y values, or f values here. These are always good ones to choose. But that one key characteristic point that we have here on every exponential function is this 0, 1. I'm going to say 0, 1. And of course, we could check this here. 3 to the 0 power is 1. In this particular case, though, to get a more accurate graph, instead of just having a graph that does this, okay, and then kind of increases, which would be the general shape of this, what we at least want to do is make sure we get at least one more point on our graph. So let's plug in 1. We say, 3 to the first power, what would we get here? We would get 3. So we say 1, 3, and just to be even more accurate, let's plug in 2. We say 3 to the second power is 9. I believe we could fit this on this grid, so we say 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, and 9 would be this point right here. So from left to right, all we're going to do is we're basically just going to sketch in this graph here. And we want to be really careful that we have a graph that is continuously getting steeper and steeper, that doesn't go kind of off to the right here like this. That's not accurate. We want a graph that's always going to be increasing. So here's our exponential growth function. We can see that its domain is negative infinity to infinity. Of course, this will be true for all exponential functions. And its range in this particular case is all values greater than 0 on the y-axis here. So now knowing kind of this basic shape of this graph, what I want to kind of bring up is the fact that we've discussed function transformations in the past. And so what we're saying is if I had some new g of x here, and it's equal to a times f of x minus h plus k, where f is the parent function, really what we're saying is g of x is just the graph of the parent function that's been changed by these values of a, h, and k. So let's make some notes here. We say h, this is our horizontal translation, or horizontal shift. And one other note that I want to make here is that it's backwards from what it appears to seem. So if this is a negative here, or it looks negative, it's really shifting to the right. And if it looks positive, it's really shifting to the left. We have here our vertical translation. So we have vertical translation. And it is honest. It does not lie. And then this a value out in front here, we have vertical stretch or shrink. Okay, I would say. And also x-axis reflections. Reflections over the x-axis if it's negative. So with all of these being known, what we should be able to do is more easily construct exponential graphs knowing that they all have an asymptote on the x-axis and they all go to the point 0, 1. What would this graph look like? So let's look at g of x over here. And what I want to bring up is that f of x equals 3 to the x is our parent function. So that was a graph that had an asymptote here on the x-axis. So y equals 0, went through the point 0, 1, and if we plug in 1, we could see that it goes through the point 1, 3. And so we have this basic shape of f of x. The real question then becomes, well, what would the graph of g of x look like? And what I notice is this 1 here, this plus 1, is inside with my x. It's kind of included with my x. So what this is going to represent is a horizontal translation, and because horizontal translation is often represented backwards, we would say that this would really just shift all of our graph left 1. So when you want to sketch graphs of exponential functions, here's how you'll do it. Just go ahead and sketch in your parent function, and then we'll do these transformations to it, which in this case means we're going to take all of our points and shift them left 1. This point would shift left 1. We could certainly label these points, and I would say that if everything shifts left 1, it doesn't affect the fact that we have a horizontal asymptote at y equals 0. So our graph this time would be just this exponential function that we graphed initially, but shifted left 1. Okay. Moving forward, we have some more transformations to consider. We say if I know what 3 to the x looks like, this f of x equals 3 to the x power, then this would be the same graph, but I notice that this has a k value this time. K being this loose term off on the side. So this is really going to take our graph and shift everything down too. So again, I'm just going to really quickly construct our parent function here. We say at y equals 0 as our horizontal asymptote. It goes to the point 0, 1. I'm going to label that 0, 1. And it goes to the point 1, 3. And I do want to label this one also 1, 3. We want to be as accurate as possible. So here's our parent function. Crawls along the asymptote here out on the edge, and then it starts to increase without bound. So when we look at this here, we say, okay, 3 to the x minus 2, really what we have is some vertical translation where all of our points are going to shift down 2 units. So we still want to label these. I would say that this is the point now 0, negative 1. This is the point 1, 1. And the only other thing we need to make sure we do is we need to shift the asymptote also downwards 2. So now the asymptote is going to be located at y equals negative 2, and we have this new function right here that grows exponentially just like that. So we would say its domain is all real numbers, and its range would be all y values greater than our asymptote value here. So now taking a look at g of x equals negative 3x. What I want to point out is this is the same thing as negative 1 times 3 to the x. That is to say that this negative has nothing to do with our exponent here. So because we have a negative out in front, what I know is whenever we have a negative out in front here, we have something that's reflected over the x-axis. So what we're going to get on this graph here would be the same as our parent function, y equals 3 to the x, which I'm sure you're probably sick of me graphing at this point. We say 0, 1 and 1, 3, 0, 1 and 1, 3. This is our parent 3 to the x function. We would say, how would this graph be affected if I said negative 3 to the x? And because we put the negative out in front here, or not in front of the x value, we put it in front of the y value, essentially what we're going to get is an x-axis reflection. So we're going to have now, instead of at 0, 1, we're going to have the point 0, negative 1. We're going to have the point, instead of 1, 3, we're going to have the point 1, negative 3. And from here we would say that it did not shift, so we still have the same horizontal asymptote. It's just that it would grow in a negative direction here. So this one would have a domain of all real numbers, domain negative infinity to infinity, and its range, as a matter of fact, would be negative infinity up to 0, but stopping right before 0. So for this last graph here, we have g of x equals 3 to the negative x. Now what I want everybody to notice is that here we put the negative in front. That is like putting our negative in front of our y values. And if you are wondering what I mean by putting it in front of our y values, we have this expression here. If we take everything times a negative, I get negative y values equals 3 to the x. So we really are kind of making our y values negative here, which flips it over the x-axis. Well, the moment we make our x values negative, now we have something that flips it over the y-axis. So if we're going to graph our parent function, again, y equals 3 to the x, where nothing's been done to it. We say 0, 1, and 1, 3 are on our graph. So we have 0, 1, and 1, 3, and this is exponential growth. So here's our growth parent function here. What we could see is that if we were to reflect this now over the y-axis, this point 1, 3 would become the point negative 1, still positive 3. And 0, 1, it actually reflects onto itself. What we would get is a graph that reflected over the y-axis would look like this. And I'm just going to admit, I'm really bad at drawing them in this direction. But what you see here is a graph that represents exponential decay, and this is something we've noted in the past. The fact is, if the coefficient of this exponential x is negative, then we have something that is going to decay as we read this from left to right. But the reason why really is because we've caused a y-axis reflection. So the last thing we want to do in this video is, without looking at the graphs of these or graphing them, could we state the transformations of g of x with respect to f of x here? So if we had some function here, f of x, and it's equal to 4 to the x, we say what would be true about the graph of 4 to the x minus 2? And I notice that is an h value there, so we would say it is shifted left. Ooh, right. It's backwards. 2 units from the graph of f of x. And then if we were to look at now this over here, we say g of x equals 4 to the negative x power plus 3. Let's start with our negative x here. Because we made our x values negative, this is going to cause a y-axis reflection. Also, we would say that because we have a k value of positive 3, it's going to shift g of x upward 3 units from the graph of f of x. So as long as we know how to graph the parent function here, y equals a to the x, we can graph all of their transformations that follow. Cheers.